Hello, and a truly warm welcome to everyone joining me today. It's so good to have you here. Before we dive into this absolutely fascinating topic, I want to take a quick moment to just say thank you for being here and to send my very best wishes to you and your family. I genuinely hope you are feeling happy, healthy, and full of positive energy today. Wherever you are tuning in from, I'm sending you a virtual hug and my best vibes. Now, let's get started on a journey that will take us to the very bottom of the ocean. Have you ever wondered about the secrets hidden in the deepest, darkest parts of our oceans? Well, today we're going to talk about one of the most incredible and surprising secrets of all. It's a fact that sounds like it's straight out of a pirate's treasure map or a science fiction novel. Are you ready? Here it is. Dissolved within the vast waters of the world's oceans, there are an estimated 20 million tons of gold. Just let that number sink in for a moment. 20 million tons. That is an almost unimaginable amount of wealth just floating there, right now, all around us. It's a concept so dazzling it captures everyone's imagination. But if that's true, why aren't we all ridiculously rich? Why isn't there a global gold rush happening in the middle of the Pacific Ocean? The story of the ocean's gold is a thrilling tale of chemistry, geology, human ambition, and, ultimately, a reality check that is more fascinating than any fiction. So, let's wade into these waters together and uncover the whole story, from why the gold is there in the first place to why it's likely going to stay there for a very, very long time. First, we need to tackle the big question. How did all that gold get into the ocean in the first place? It didn't just appear there by magic. The story begins with the Earth itself. Gold, the element, has been a part of our planet since its very formation. It's scattered throughout the Earth's crust, locked up inside rocks and minerals. Over millions of years, natural weathering processes are constantly at work. Rain, which is slightly acidic, falls on rocks containing tiny traces of gold. Wind erodes the rock surfaces. Freezing and thawing cycles crack rocks apart. This relentless natural assault slowly breaks down these rocks, and in the process, minute particles of gold are released. These tiny particles are then washed away by rainwater, joining streams and rivers that eventually, after a long journey, empty into the vast oceans. This is one of the primary natural delivery systems, constantly feeding a very dilute soup of gold and other minerals into the sea. But there's another, even more dramatic delivery method. Think about the bottom of the ocean. It's not a quiet, still place. It's geologically active, with volcanic vents, fissures, and hydrothermal systems constantly releasing superheated water that has been circulating through the Earth's crust. This hot water is incredibly effective at dissolving minerals, including gold, from the rocks it passes through. When these hydrothermal vents, often called black smokers, spew their mineral-rich plumes into the cold ocean water, the dissolved minerals rapidly precipitate out, forming spectacular chimney-like structures and clouds of particles. A significant amount of gold is delivered directly into the ocean water column from these deep-sea vents. So, between the surface runoff from land and the volcanic activity from below, the ocean has been receiving a steady, slow infusion of gold for billions of years, building up to that staggering total of 20 million tons. Now, here's the part that is most crucial to understand, and it's the part that most people often miss when they first hear this fact. That gold is not just sitting on the seafloor in neat, shiny piles of gold bars or easy-to-grab nuggets. It's not like a sunken treasure ship where the gold is concentrated in one place. The 20 million tons figure is a measurement of the total mass of gold, but it tells us nothing about its concentration. And concentration is everything. The gold is dissolved in the seawater. It exists as incredibly tiny particles, often on the atomic or molecular scale, spread evenly throughout the entire world's oceans. Imagine you took a single pinch of table salt and dropped it into an Olympic-sized swimming pool. You would know the salt is in there, but if you scooped up a glass of that water and tasted it, you would never know. The salt would be so spread out that your tongue couldn't detect it. The gold in the ocean is like that, but even more dilute. Scientists estimate that on average, a single liter of seawater, that's about what you'd fill a large water bottle with, contains only about 13 billionths of a gram of gold. To put that in perspective, you would need to process millions of liters of seawater just to collect enough gold to make a single, small wedding ring. The ocean is vast beyond comprehension, and it's that vastness that adds up to 20 million tons, but it's the extreme dilution that makes it so elusive. This leads us directly to the next big question. If it's so dilute, how do we even know it's there? How did scientists come up with that number? This is a brilliant story of human ingenuity and precise measurement. You can't just dip a bucket into the ocean and see the gold. Detecting gold at these unbelievably low concentrations is a monumental scientific challenge. The process begins with collecting water samples from all over the world, from different depths and different ocean basins. This in itself is a huge undertaking, requiring research vessels and specialized equipment like Niskin bottles that can capture water samples from specific depths without contaminating them. Once a sample is brought on board, the real magic, or rather, the real chemistry, begins. The scientists face the task of finding a few atoms of gold in a liter of water that is filled with massive amounts of other dissolved substances, primarily sodium chloride, which is common table salt, but also magnesium, calcium, potassium, and dozens of other elements. The first step is usually pre-concentration. They might add a tiny amount of a special chemical that has a known attraction to gold ions, causing the minuscule gold particles to cling to it. Or they might use a technique called solvent extraction. After this initial step, they are left with a much smaller sample, but one that is still a complex mixture. To finally measure the gold content, they rely on incredibly sensitive modern instruments. One of the most common is a machine called an inductively coupled plasma mass spectrometer. Now, that sounds incredibly complicated, and it is, but the basic idea is this. The machine turns the sample into a superhot plasma, essentially a gas that is so energized that it breaks down all the molecules into their individual atoms. Then, it uses powerful magnets and electric fields to sort these atoms by their weight. Since gold atoms have a unique and very specific atomic mass, the machine can count them one by one. It's like finding a single specific person in a stadium filled with millions of people by knowing their exact weight down to the most precise measurement possible. It's an astonishing feat of technology that allows us to confidently say, yes, the gold is there, and we know, on average, how much is in any given volume. Knowing the gold is there and that there's a vast total amount has, unsurprisingly, driven people to try and get it out. The history of attempts to extract gold from seawater is a long and colorful one, filled with brilliant minds, ambitious entrepreneurs, and, ultimately, spectacular failures. The most famous episode began just after World War I. A famous German chemist named Fritz Haber, who had won the Nobel Prize for his process to create ammonia from nitrogen and hydrogen, which revolutionized fertilizer production, turned his attention to this problem. Germany was buried in war debt and reparations from the Treaty of Versailles, and Haber, a patriot, became obsessed with the idea of single-handedly restoring his country's finances by extracting gold from the sea. He devoted years to this project, embarking on a meticulous and secretive research voyage across the Atlantic to collect water samples and develop a complex extraction process. His team developed advanced methods for analysis, but after years of work and immense effort, the results were devastating. The concentration of gold in the seawater was far, far lower than previous, less accurate estimates had suggested. His process would have cost vastly more to run than the value of the gold it could possibly recover. The dream of saving Germany with ocean gold evaporated. This pattern has repeated itself throughout the 20th century. Numerous inventors have claimed to have devised the perfect method, only for their schemes to collapse under the weight of economic reality. The fundamental problem is always the same. The energy and chemical costs of processing the absolutely colossal volumes of water required to get a tiny amount of gold are simply too high. You would need to build unimaginably huge processing plants that suck in ocean water by the millions of gallons per minute, and the electricity bill alone would be many times greater than the value of the gold you'd recover. It is, and has always been, a financial losing proposition. But what about the future? Could new technology ever make this feasible? This is where the plot thickens beyond just the simple concentration problem. Even if someone invented a magical filter that could effortlessly pluck gold atoms out of seawater with no energy cost, there are other massive hurdles. The first is the sheer engineering challenge. The ocean is a brutal environment. Saltwater is highly corrosive. Building and maintaining any large-scale structure in the open ocean is phenomenally expensive and difficult. Storms, waves, and biofouling, where sea life like barnacles and algae quickly cover any surface, would constantly threaten operations. The second, and perhaps even bigger, hurdle is environmental. The process of sucking in millions of gallons of seawater per minute is not harmless. This seawater is full of life. It contains plankton, which are the very base of the marine food web. It contains fish eggs and larval forms of countless marine organisms. Any large-scale intake pipe would act like a giant vacuum cleaner, indiscriminately killing immense amounts of ocean life. The water you would eventually pump back out would also be changed. Its temperature and chemical composition might be altered, potentially creating dead zones around the outflow pipes. The environmental impact of a full-scale ocean gold mining operation would likely be catastrophic for local marine ecosystems, and the ethical and regulatory barriers would be enormous. So, the challenges are not just economic and technological, they are also profoundly ecological. This brings us to a very important distinction. While extracting gold from the water column itself is impractical, there is another place in the ocean where gold is found in much higher, and therefore more tempting, concentrations on the seafloor. We are talking about deep-sea mining. On the bottom of the ocean, particularly in certain areas like the Pacific Ocean's Clarion-Clipperton Zone, there are strange formations called polymetallic nodules. These are potato-sized lumps of rock that form over millions of years as metals slowly precipitate out of the seawater and accumulate around a core, like a shark's tooth or a piece of ancient debris. These nodules are rich in manganese, nickel, copper, cobalt, and yes, they also contain traces of gold and other precious metals. There are also massive sulfide deposits around hydrothermal vents, which can be incredibly rich in gold and silver. The concentration of gold in these seafloor deposits is orders of magnitude higher than it is in the water itself. This is where the real modern-day ocean gold rush is focused. Companies are actively developing giant robotic machines designed to crawl along the deep seabed, vacuuming up these nodules or grinding down sulfide structures. The technology is being tested now. However, this comes with its own set of immense environmental concerns. The deep sea floor is one of the least understood ecosystems on Earth. We are only just beginning to discover the strange and wonderful life forms that live there, many of which are incredibly slow-growing and vulnerable. The process of mining would not only destroy the immediate area, but also create giant, sediment-laden plumes of water that could drift for miles, smothering life wherever they settle. The environmental debate over deep-sea mining is fierce and ongoing, and it's a stark reminder that even if the gold is easier to get to, getting it out responsibly is a whole different challenge. So, where does this leave us? We are surrounded by an ocean containing a fortune in gold, but it's a fortune that is forever out of practical reach. It's a beautiful paradox. That 20 million tons of gold serves as a powerful reminder of the sheer scale and power of the natural world. The ocean is so immense that it can hold a king's ransom in every cubic mile and yet keep it hidden from us, not by locking it away in a chest, but by spreading it so thin that it mocks our attempts to possess it. It teaches us a lesson about resources and value. Just because something exists in great abundance does not mean it is accessible or practical to use. It's a lesson in humility for us as a species. For now and for the foreseeable future, the ocean's gold will remain where it is, a dazzling secret held in solution, a dream of wealth that fuels our imagination but ultimately protects itself from our greed through the brilliant, simple defense of dilution. It is the world's greatest treasure guard, and perhaps that's exactly how it should stay. Thank you so much for exploring this amazing topic with me today. I hope you learned something new and fascinating.